Welcome to the Astro Guy podcast. I'm your host, Wayne Zool. In this episode of our Great Astronomers Series, we're stepping into the quiet, meticulous world of a woman whose work reshaped the way that we measure the universe. You may not recognize her name immediately, but without her, Edwin Hubble couldn't have proven that the universe is expanding. Without her, we wouldn't know the distances to galaxies beyond our own. She didn't hold a professorship, she never built a telescope, and she didn't publish a grand theory. Yet, without her work, much of what we know about the size and structure of the universe would still be unknown. This is the story of Henrietta Swan Leavitt, a quiet, determined woman who uncovered a pattern in the stars that would forever change our understanding of the cosmos. Henrietta Swan Leavitt was born on July 4th, 1868, in the small town of Lancaster, Massachusetts. It was a time of great change in America. The Civil War had just ended 3 years earlier. The Transcontinental Railroad was under construction. Thomas Edison was still a young boy. As the daughter of a congregational minister, she grew up in a family that valued education and faith. She was quiet, studious, and deeply curious about the world. She was the oldest of 7 children. Growing up in a busy household, she found solace in books and ideas. Even at a young age, she showed a love for patterns and precision, traits that would serve her well later in life. The family moved several times as her father took positions in Iowa and then later back in Massachusetts. As a young woman, Henrietta attended Oberlin College in Ohio, one of the first coeducational colleges in the United States. It was here that she received a broad education, studying literature, classical languages, music, and mathematics. Although she didn't complete her degree right away due to an illness, she returned and graduated in 1893. That same year, she began working as a volunteer at the Harvard College Observatory. Earlier, in 1888, she transferred to what was then called the Society for the Collegiate Instruction of Women, which would eventually become what we know as Radcliffe College. It was Harvard's coordinate school for women, a place where female students could receive instruction from Harvard professors, but not attain their degrees from Harvard. At Radcliffe, Henrietta encountered astronomy for the first time in any formal sense. Among her courses was one that included observational and laboratory work at the Harvard College Observatory, where students examined photographic plates and worked with data from actual telescopic observations. For many, it was just another science requirement. For Henrietta, it lit a spark in her that never went out. There was something about the precise, almost meditative process of measuring starlight, light that had traveled across vast gulfs of space and time, that deeply resonated with her. The patterns, the order, the quiet complexity of it spoke to both her scientific mind and her introspective nature. She wasn't just memorizing facts or solving textbook problems. She was touching the sky, one data point at a time. But after graduating in 1892, life took a turn. Like so many women of her time, there were limited paths open to her, especially in science. Worse, Henrietta's health began to fail. An illness, possibly scarlet fever or meningitis, left her increasingly deaf. It would ultimately become profound hearing loss. This might have ended her scientific aspirations altogether, but Henrietta didn't let it. For a few years, she drifted quietly. She traveled in Europe, lived with family, and continued her studies on her own. Then, in 1895, she returned to Harvard College Observatory, this time not as a student, but as a volunteer assistant. She would soon become one of the most important figures in the observatory's history. Now, to understand Henrietta's role, we have to talk about the team she joined, which was known as the Harvard Computers. Under the direction of Edward Charles Pickering, the Harvard College Observatory was pioneering a revolutionary new method of observing the sky. Instead of simply sketching celestial objects by eye, they were using photographic plates, thin sheets of glass coated in a light-sensitive emulsion to capture the night sky in great detail. This process allowed for a far more permanent and precise record than visual observations, but it created an avalanche of data, thousands of plates, millions of stars. All of them needed to be examined, measured, and cataloged. Pickering had a problem. He didn't have the manpower to analyze this treasure trove of data. So, in a move that was progressive for the time, and to be honest, Also exploitative, he hired women, dozens of them. They were highly educated, meticulous, and far less expensive to employ than men. These women were officially known as computers. Today, we might call them data analysts, but their work was anything but simple. They measured star positions, classified stellar spectra, and studied changes in brightness over time. They worked at long tables in a room filled with gas lamps and the smell of photographic chemicals, bent over magnifying lenses and slide rules, carefully logging their findings in neat handwriting. Henrietta was one of them. She began her paid work at the observatory in 1902, earning just 30 cents an hour. That's roughly the equivalent of about $10 an hour today. Hardly a living wage, even then, but the work itself was enough for Henrietta. Unlike some of her colleagues who focused on stellar classification, most notably Annie Jump Cannon, who developed the Harvard classification scheme still in use today, Henrietta's work took a different path. Cannon was a brilliant and tireless classifier, credited with cataloging more than 350,000 stars and refining the spectral classification system into the now familiar OBAFGKM sequence based on a star's temperature and its spectral lines. But while Annie was organizing the stars, Henrietta was measuring their behavior, watching how their brightness changed over time, and searching for hidden patterns in their variability. Both women worked with the same tools, glass plates, magnifying glasses, and meticulous attention to detail, but their discoveries illuminated different aspects of the universe. Henrietta took a particular interest in variable stars. These are stars whose brightnesses change over time, sometimes very subtly, other times in dramatic fashion. Henrietta was assigned to analyze variable stars in the Magellanic Clouds, which are two small satellite galaxies of the Milky Way that are mostly visible from the southern hemisphere. Luckily, Harvard had photographic plates from an observatory in Peru, giving Henrietta access to decades of observations. She would spend countless hours cataloging these stars, day after day, week after week, year after year, meticulously recording data from fragile glass plates, only using a magnifying eyepiece, a ruler, and a sharp pencil. Her task was deceptively simple. Measure the brightness of each variable star at different points in time, then calculate how long it took that star to complete a full cycle of dimming and brightening. The work was tedious, repetitive, often done in silence, but Henrietta found meaning in the precision. Where others might have seen noise, she was looking for structure, and then, after years of labor, she saw it, a pattern. In the flickering lights of the small Magellanic Cloud, she began to notice something remarkable. As she charted the periods, the time it took for each star to pulse from bright to dim and back again, and then compared them to their apparent brightness, a pattern began to emerge. It wasn't random. The longer the period of pulsation, the brighter the star appeared to be. It was subtle at first, but it was consistent. And Henrietta realized this wasn't just a strange correlation, it was a breakthrough, a way to measure not just the brightness of a star, but its true intrinsic luminosity. What Henrietta discovered was nothing less than a cosmic yardstick, a reliable method to measure distances across the universe. Henrietta had found a relationship between two things: how long a Cepheid variable star took to complete a cycle of brightness changes, its period, and how bright the star truly was, its absolute magnitude. This meant that if you could measure the period of a Cepheid's pulsation, you could determine its intrinsic brightness, and once you knew that, you could compare it to how bright the star appeared from Earth and calculate how far away it must be. This may sound simple today, but at the time it was revolutionary. Remember, at the start of the 20th century, astronomy was still struggling to grasp the true scale of the universe. Astronomers had developed a method called parallax to measure the distances to a few of the nearest stars by observing how those stars appeared to shift slightly against the background sky as the Earth orbited the Sun. But parallax only works for relatively close objects, and even with the best instruments of the day, that limit was just a few hundred light years. Beyond that, it was simply guesswork. There were no calibrated tools for measuring the distance to most stars, let alone to the faint fuzzy patches of light that filled the night sky. Some of those distant smudges were nebulae within our own galaxy. Others, like the Andromeda Nebula, were suspected by a few bold thinkers to be island universes, entire galaxies in their own right, but there was no way to prove it. Even the size of the Milky Way itself was unknown. Some astronomers thought the entire universe might be just a few thousand light years across. Others argued for hundreds of thousands, but without any kind of cosmic yardstick, there was no way to check. Into that void of knowledge came Henrietta Leavitt's discovery, a reliable, repeatable relationship between a star's brightness and its period. She didn't know it at the time, but she had just handed the astronomical community its first real tool to measure distances far beyond the reach of what parallax could measure. She gave them a way to truly scale the universe. By observing Cepheid variables in the small Magellanic Cloud, she had a brilliant insight. Because all of these stars were in roughly the same location in space, they were all about the same distance from Earth. That meant that any difference in their apparent brightness had to be due to true differences in luminosity, not distance. This eliminated a huge variable and allowed her to isolate the correlation between brightness and period. In 1908, she published her findings in the Annals of the Astronomical Observatory of Harvard College. The paper was titled simply 1,777 Variables in the Magellanic Clouds. And buried within it, almost as an aside, was one of the most important statements in the history of astronomy. It is worthy of notice that the brighter variables have the longer periods. Worthy of notice indeed. It was a quietly phrased observation, which was typical of Henrietta's modest style, but it laid the foundation for an entirely new way of measuring distances. Her variable stars would become the standard candles of the universe, objects whose intrinsic brightness is known, allowing their distance to be determined with remarkable accuracy. Pickering, her supervisor at Harvard, published a summary of her work in a 1912 article in the Harvard College Observatory Circular, formally crediting her with the discovery of the period-luminosity relationship. But even then, the implications hadn't fully sunk in. It would take another decade and another great astronomer for the world to realize just how far her discovery could reach. Sadly, Henrietta Leavitt passed away in 1921 at the age of 53 following a long illness. She never held a professorship, she never led an observatory, and she never received a major award during her lifetime, and she never knew just how far her quiet discovery would reach. But a few years later, another astronomer would take that work and use it to change our understanding of the universe forever. That astronomer was Edwin Hubble. In the early 1920s, Hubble was working with the 100-inch Hooker telescope at Mount Wilson Observatory in California. At the time, it was the largest and most powerful telescope on Earth, capable of revealing stars and objects far beyond the reach of earlier instruments. Hubble was fascinated by the Andromeda Nebula, a fuzzy patch of light visible even to the naked eye. For centuries, astronomers had debated whether Andromeda was simply a nearby cloud of gas inside the Milky Way, or something more. Then, in 1923, Hubble spotted a Cepheid variable star within Andromeda, and not just one. He would go on to identify dozens of them. Using Leavitt's period-luminosity relationship, he measured their pulsation periods, determined their true luminosities, and compared them to how bright they appeared from Earth. The result was stunning. Andromeda wasn't thousands of light years away. It was more than 2 million light years distant, far beyond the outer reaches of the Milky Way. This was the breakthrough. Hubble had just proven that Andromeda was a galaxy in its own right. He had just proven that it was one of many in a much larger universe. In a 1925 lecture at the Royal Astronomical Society, Hubble stated plainly, "Our galaxy is one of millions." The universe was far larger and far more populated than anyone had realized. But Hubble didn't stop there. Over the next few years, he used Leavitt's method to measure the distances to more and more galaxies, and he noticed something else. The farther away a galaxy was, the faster it appeared to be receding from us. In 1929, he published what would become one of the most important papers in the history of science, revealing what we now call Hubble's law, which states that galaxies are moving away from us at speeds proportional to their distances. This discovery led directly to the development of the Big Bang Theory and marked the beginning of modern cosmology. And behind that discovery, quietly and unmistakably, was the work of Henrietta Leavitt. Hubble himself acknowledged her contribution, writing in 1929, "The outstanding work on the period-luminosity relation is that of Miss Leavitt, and it is to her that the credit primarily belongs." In 1931, the Swedish mathematician Gustav Middag Leffler even wrote to the director of the Harvard Observatory to ask if Leavitt could be nominated for the Nobel Prize in Physics. He was told, sadly, that she had died 10 years earlier. The Nobel Prize is not awarded posthumously. So the recognition she so richly deserved never came in her lifetime. But make no mistake, Henrietta Leavitt handed astronomy its first reliable cosmic yardstick. She gave astronomers the tool to measure the universe, one variable star at a time. Without her, there would be no Hubble's law, no understanding of cosmic expansion, no map of the observable universe. She didn't live to see it, but she had already drawn the blueprint. In her lifetime, she remained largely unknown outside of the Harvard Observatory. She received no major scientific awards, no public honors. Even within academic circles, she was often referred to simply as one of Pickering's computers. But in the decades after her death, the importance of her work only grew. Her period-luminosity relationship became one of the foundational tools of observational cosmology. Every major discovery involving the scale and structure of the universe, from the distance to galaxies, to the rate of expansion, to the calibration of supernovae as standard candles, can trace its roots directly back to her insight. In many ways, Henrietta Leavitt was ahead of her time. Her quiet, precise brilliance didn't fit the mold of the early 20th century scientist. She didn't seek the spotlight, and for many years, history returned the favor by keeping her in the shadows. But today, astronomers know better. In 1973, the International Astronomical Union named crater Leavitt on the far side of the moon in her honor. A minor planet, 5383 Leavitt, also bears her name, quietly orbiting the sun between Mars and Jupiter. Several books, documentaries, and plays have brought her story to life, including the spectacular book by David Sobel, The Glass Universe, and Lauren Gunderson's play Silent Sky, which centers on Leavitt's life and legacy. The play has introduced thousands of theatergoers to the woman who measured the stars. Her work has also been recognized by professional astronomers, and perhaps most significantly, her name now appears where it belongs, in textbooks, planetarium lectures, astronomy courses, and scientific histories, as the scientist who first showed us how to measure cosmic distances. Henrietta Swan Leavitt never set out to change the universe. She didn't command observatories or lead expeditions. She didn't lecture in packed halls or collect awards during her lifetime. Her work was done in quiet, dimly lit rooms, surrounded by stacks of photographic plates and worn notebooks, carefully measuring the light of distant stars, one observation at a time, guided more by patience and precision rather than by recognition. And yet, in that silence, she changed everything. Leavitt's discovery of the period-luminosity relationship of Cepheid variable stars wasn't a lucky guess. It was the result of her patience, precision, and a mind that was well honed for pattern recognition. She saw what others had overlooked, a direct link between a star's brightness cycle and its intrinsic luminosity. She didn't build great telescopes, but she gave those who did the scale to measure what they saw. In a time when women in science were often treated as assistants, denied credit, and paid less than their male peers, Leavitt persisted. She remained focused, not on recognition, but on the work. And the work, her careful, methodical, unglamorous work, laid the foundation for some of the greatest discoveries in astronomy. "A straight piece of wood is useful," she once wrote in a rare personal letter, "because it shows the curve of what surrounds it." Henrietta Leavitt died in 1921 at the age of 53 from stomach cancer, never knowing the full extent of her legacy. Today, every time we speak of the expanding universe, galaxies racing away, the observable cosmos stretching billions of light years across, we are also speaking of Henrietta Swan Leavitt, because she didn't just measure the stars, she gave us a way to measure the universe. And that's what science is at its best, a collective story written by curious minds, each adding their own chapter. Some get headlines, others, like Leavitt, write in the margins, but without them, the story would be incomplete. So when we gaze up at the night sky, let's remember the quiet revolution that she sparked. And let's honor it by continuing to ask questions, to look deeper, and to never stop being curious. Thanks so much for joining me for this most recent installment in our Great Astronomers series. I hope Henrietta Leavitt's story was as inspiring and eye-opening for you as it was for me to share. If you've got questions, thoughts, or suggestions for future episodes, I'd love to hear from you. Please email me at astroguypodcast@gmail.com or leave a text or a voicemail at 973-404-0380. Be sure to join the conversation in the Astro Guy Podcast group on Facebook, and check out our YouTube channel for past episodes, live imaging sessions, and exclusive bonus content. If you've enjoyed this episode, please take a moment to like, subscribe, comment, and share. It really helps to let people know that we're here. And if you'd like to support the show, you can always buy us a cup of coffee. Your generosity helps keep the microphones on and the telescopes tracking. You'll find the link in the show notes. Until next time, may your skies be clear, and as always, carpe noctem, seize the night. I'm Wayne Zool, and this was the Astro Guy Podcast. Thank you for listening. As always, your questions, comments, and suggestions are welcome. Keep wondering. Keep your eyes on the sky. Have fun. Carpe noctem. Seize the night.